Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue to talk about Lasso. In previous video, we discussed the intuition, and in this video, we look at the implementation of Lasso, LassoCV, and the multitask Lasso. So let's get into Jupyter Notebook and implement these. So here, these are the libraries I've imported: NumPy, pre-processing data sets, linear underscore model, and then we'll need the train test split as well as matrix. And for plotting, we have the matplotlib. And these are the versions that I'm using right now. Now, the first item that we'll look at is just a simple lasso fit and see how it can drop features. So for this, we'll use the Boston dataset and get that data. We can type data is equal to datasets dot load underscore Boston, and then uh, once that is loaded, we can use the train test split to get the parts for X train and Y train. X train, then X underscore test, Y underscore train, Y underscore test is equal to train underscore train test split. So train underscore test underscore split, and then you have data, then data.target. The reason why it's data.data is because this data variable, let's run this first. Now you look at data, it's a dictionary, and within this dictionary the data is in this uh, all aligned with the key array, and the target is aligned with the key target, and that's why we have those there. Next, for Lasso, we'll compare this with Ridge as well. So when creating the variable, I'll use underscore Lasso for this, so we know it's for the Lasso fit. We have linear underscore model dot Lasso with a capital L. Then we'll set the alpha to 0.1, and we'll have the normalize is equal to true. Next, we'll need to fit this. So reg underscore lasso dot fit, and for fit we'll use the x underscore train, y underscore train, and now we can look at the coefficients. So we can also go ahead and print those. Print total coefficients, and here we can look at the length of uh, reg underscore lasso dot coef underscore. So that's where the coefficients are stored, and then we can look at the number of non-zero coefficients as well. So where I'm going with this is Lasso, if you remember from previous video, it removes it zeros some of the features uh, by zeroing the parameters. And so what we are looking here is the parameters or coefficients that are zero. Can we see those when we implement Lasso? Non-zero coefficients is equal to np.count underscore non-zero, and here again we specify reg underscore lasso dot coef underscore. When we run this, there are total 13 coefficients, so we can look at those. Reg underscore lasso dot coef, and these are the 13 coefficients, and among these uh, there are three non-zero coefficients. Just three coefficients are non-zero, and all the remaining coefficients are zeroed out. And if we want to check which those parameters are features are, can do that. So we can say data dot feature underscore names, and here we can see that 1 2 3 4 5 sixth parameter is non-zero. So 1 2 3 4 5 6, so this one is non-zero, and then the last one, which is the LSTAT, that is non-zero, and the one before that, so PT ratio, that is non-zero. Rest all others have are zeroed out. Now moving on, let's look at what Ridge would have done if we had applied the same model there. I'll copy this, paste it here, and here I'm going to say reg underscore ridge, and here we are going to use the ridge model. We'll keep the same alpha so that we can compare between the two. And again, for the coefficients, we need to specify ridge here because that's the model we are using for saving the coefficients. And here, as you can see, none of the coefficients are zero, and we can look at the coefficients OEF, and as you can see, let's round those, so dot round to 2 decimal places, and as you can see, they are not zero, and these are uh, in decimals, so they are less than 1, closer to 0, but this one is not closer to 0, and this absolute value of these two are also not closer to 0, even though they are zeroed out in the lasso. So that's just something to remember, and we'll see what impact that can have. Maybe it could help improve accuracy in this particular example. Maybe dropping that feature may affect the accuracy. We'll take a look at that. So what we can do now is we can calculate the predictions on the test set. So y underscore pred underscore lasso, and we'll get that for the train as well as the test. Reg underscore lasso dot predict, and here we'll use the train set. Then after this, we'll use the test set. So this would be on the test. Again, this would be on. Similarly, uh, we need to find this for the ridge as well. So I'm going to just change this to ridge. That here, so that's for ridge, and this would be for ridge as well. Okay, so we have run the predictions. Now it's time to print those. So print first is lasso, and for lasso, let's look at the train MSE, what it is, and then we'll also look at the test MSE. We'll use the matrix dot mean underscore squared underscore error for this one, and we need to specify y underscore train because this is for the train prediction. Yeah, y underscore pred underscore lasso underscore train, and then we copy this and create another line with instead of train this time we'll use test, and just I'm changing these words here for test. So that is for lasso, and now after that we'll create the same print statements for ridge, one each for the train as well as the test set. So we have ridge here, copy that here. So that should be matrix. Okay, and there's another error that for an inconsistent number of samples. I probably made a mistake. Y train, uh, and then we have lasso. Okay, and that's because this needs test. Sorry about that. Because we are comparing the test predicted with y test in both the cases. Okay, so here as we can see, get a line. Here we can see that the train MSE is lower in case of train MSE is better for ridge as compared to lasso. If you remember, lower the MSE, the better it is. So 0 MSE is the best. It means that there's no difference between your predicted and the actual value. So here there is a residual of 19, so MSE of 19, whereas here there is a higher MAC. Now, when we look at the test data, test MAC, again the MAC is lower for Ridge as compared to the Lasso. And the reason why that may be the case because Ridge is using more parameters than Lasso, because Lasso zeroed out almost everything. One another item that we can try to check is if we change the value of alpha to zero point 0.5. Let's see if that changes anything. Okay, with 0.5 everything is zeroed out. So let's see if we can reduce the alpha value and change that to 0.005. Now both of them have 13 non-zeros, and in this case if we look at the predictions, they are pretty close. They're 19 and 32, 19 and 31. So uh, tuning the alpha parameter for Lasso would be very important based on this. And cross validation can help achieve that. So let's now look at cross validation, or C. And here we'll use the same example that we have been going above. So only changes we'll do is we'll create a new parameter, lasso, new variable, lasso CV is equal to linear underscore model dot lasso CV. And here we'll specify alphas. So alphas is equal to, we'll start with 0.001, maybe 0.01, 0.1, and then 1. And after this we'll also use normalize is equal to true. And once we have that, we can use that to fit reg underscore lasso cv dot fit, and we use the x underscore train and y underscore train similar to this. So let's label this. So this is lasso cv, and similar to this we know there is RidgeCV, so why don't we compare with RidgeCV as well. So let's go ahead and copy this because it's going to be the same line of code. Ridge, and here this is going to be Ridge with a capital R, and again this will be Ridge. So we have now done the fit with Lasso CV as well as Ridge CV. Now let's try to predict. So for predictions, we will be using the same code. So I'll copy this and paste it here. The only changes would be we need to introduce the CV because this is for the cross validation that we are working on, and predict on X train, predict on X test. That says the same in both cases. And also, when we print out the MAC, uh, this will be for CV, so we need to change that here. So this is Lasso CV train. We need to change that. Same thing for Ridge. Now, when we run this, and this is for CV, so let's add CV here as well, just so we know that this is different output. The red lasso, because we did not run that yet. Okay, and as you can see, with the value of point these values, the optimal that alpha that was chosen uh, gives us these as the train MAC, and they are looks like they are pretty close to what we had before, 1932, 1931. In this case it's 1931 and 1931 in both cases. So that's how the Lasso CV compares with the Ridge CV. Now let's look at the multitask lasso. Multitask lasso. So capital M, capital T, and capital L. With this, trying to create a markup cell. Okay. And for this, we'll use the same data set uh, which is the Boston data set, with one change. So we already have it uh, created in the data variable, but this time we'll import it differently. We'll create x comma y is equal to data sets dot load underscore Boston, and here we'll say return a underscore x capital X underscore small y is equal to true. And what that does is it gives us the data in this x and y matrices right here. So now if you remember, for multitask lasso, the y is a matrix and there are multiple outputs. So right now we just have one output here, and to add what we'll do is we'll copy column y 3 times. So just for demo purposes, that should work. So y is equal to y. First we'll add an axis, np.new axis, and so now if you look at the y dot shape, see that one there. So this means that there are 506 rows and there's one column. Now you can go ahead and concatenate that. So y is equal to np dot concatenate, and here we'll use y, and then we'll square y, or maybe just multiply by 2, then again multiply by 3, and we need to concatenate the along columns. So that's why we have axis is equal to 1. Now if we look at the y dot shape, we can see that this has 3 columns. So let me run this again. Okay, now we have this. We have 3 columns and 506 rows. So for multitask lasso, we are going to compute the 3 outputs and without using any for loops. So for this, we can look at the execution time by using time percent time, and here if we first one try multitask lasso, I will create a variable reg is equal to linear underscore model dot multitask lasso, and here we'll use the alpha value. So let's say alpha is equal to 0.5, and we'll use the same value with the lasso as well. So m lasso for multi-lasso is equal to reg dot fit x comma y, and then we'll look at the m lasso dot coefficients, so coef underscore dot shape, and here we see that it takes around a wall time of around 1.41 milliseconds. Let's look at lasso, and we are going to time this as well. So time, and this is lasso, and here we are going to use a for loop. So lasso underscore coef, that's where we'll store the coefficients, and with list comprehension we'll use for yi in y dot t. So we are taking a transpose of y. Here we'll do the fit and get the coefficient. So linear underscore model dot lasso, and we have alpha is equal to 0.5 dot fit on x and y, and then we get the coefficients coef underscore, and this needs to be yi because we are fitting on each output one at a time and then storing it in the variable lasso underscore coefficient, and here we'll convert this to an array so we can get the shape for the output. So lasso underscore coef dot shape, and here as you can see it takes around 2.67 milliseconds. So the multitask lasso is considerably faster, at least in this example, as compared to the regular lasso. Now before ending this video, I just want to show another cool trick where we can plot the zeroed coefficients in a very easy way. So you can type plt.spy, and here if you type lasso underscore coefficient, and then run this. So on the y-axis, so let's label this. So plt dot y label. So those are the tasks. So each output is considered as a task. So we have 3 columns in y. So there were 3 different output tasks to be completed, and so that is for the y-axis. And then on the x-axis, so x label, those are the features. So if you type features, and when we run this, so these are the features, and the features, uh, these features are 0. So we can run this COEF, and we can suppress that np dot set underscore print options, and suppress is equal to true. And here we can round these 2 decimal places, and here now we can see that these two are zeroed out. So 0 1 2, so those 0 1 2, those are black, so those are non-zero. And then we have these two that are 0 right here. I wonder why this is okay. That is 0 here. As let's maybe if we put 4 decimals, okay, so that is not 0. It has 0036 right there. So only these two are 0, and those two appear there as 0 in the plot. Now, similar to this, we can also go ahead and plot the coefficients for the multitask lasso. So let's try mlasso.coef, and here we can see that lesser are 0. So I'm going to copy this, paste it here. So again, let's round this around to 4 decimals, and we can see that in this first one there is only 1 0 at 0 1 2 3 4. So that's the one that's 0 in all the cases. So that's the difference between multitask lasso and lasso. I hope in this video you learned about the implementation of Lasso, LassoCV, and MultiTaskLasso, and also their comparison with Ridge and RidgeCV, how they work. In the next video, we'll continue this discussion in linear models and look at some new methods. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.